In this video, I introduce vision transformer vector quantization GAN for high-resolution image synthesis. Vision transformer vector quantization GAN consists of two components, namely vector-quantized image modeling, pre-trains the transformer to generate a better codebook autoregressively. And ViT-VQ-GAN uses the codebook to generate the reconstruction image as shown here. This is the architecture of ViT-VQ-GAN. This is the ViT-VQ-GAN model, and this is a vector quantized image modeling model. This is the encoder, this decoder, and this discriminator. This autoregressive transformer. The classes here are used in conditioned image synthesis. This codebook. The VQ training objective is defined as here, which includes two terms, namely codebook loss and commitment loss. Where SG is the identity operator in forward path, the slope gradient in backward path, namely SE serves as a reference to compute the difference in codebook encoding, but doesn't propagate. Likewise, SGE serves as a reference to compute the difference in encoder, but doesn't propagate as shown here. This encoder, this code optimization. In forward, this E is ZE. In backward, this stop gradient, this stop gradient. Training the encoder and the codebook embedding jointly minimizes the vector quantization loss. The quantized codebook index is determined by looking up the codebook vector closest to input features, ZE in terms of distance, as shown here, which requires using a straight-through gradient due to non-differentiable loss, LVQ. The ViT-VQ-GAN loss includes logit Laplace loss, L2 loss, perceptual loss, and GAN loss as shown here, where the weights are configured with a hyperparameter sweep to optimize image reconstruction quality, codebook usage, FID, and inception score. The logit Laplace loss contributes to codebook usage, while L2 loss and the perceptual loss significantly contribute to FID. With the learned ViT-VQ-GAN, images are encoded into discrete latent IDs flattened in the raster order. A decoder-only transformer model is used to model the density P of image data autoregressively, as shown here, where theta is the learnable weight. The training objective is to minimize the negative log likelihood of the data, as shown here. This autoregressive transformer with causal mask, this input and this output, this mask. For more details, please check with these references. Thank you. Bye.